Okay. So, sorry, it is in English, not in Chinese, and I will do my best to be clear. Oops. First of all, I would like to thank the organizers of this series of conferences for inviting me. It's a real pleasure for me to be here today to share with you my passion for my work, in fact. And I will begin my presentation by briefly introduce myself. You may have read in my short biography that I work at the Astronomical Data Center at Strasbourg in France as technical director. And my main investment over these 25 years has been on the project called Aladin. But behind this biography, the element that must characterize me is really my passion for programming and developing computer applications. And I must say that I was born in the right century. I started my career when the internet was just beginning. And all the developments that I am going to present are totally based on this tremendous global innovation and its evolution. And in fact, if I can talk to you from my small village in France to China's countries, thanks to the internet, the magic of the internet. And the fact that I am having all this in the discipline of astronomy in the Centre de Données Astronomiques was, for me, an undeniable opportunity. So, let me introduce a little bit the Strasbourg Astronomical Data Center. It was founded in 1972 by the French Ministry of the Education and Research, and it has been carrying out its mission for almost 50 years, so it's a long story. And since its creation, its main mission, written in its charter, has been to collect useful data on astronomical objects in electronic form, 50 years ago, improve them by critically evaluating them and combine them, and finally distribute the result to the international community. And in fact, we are quite close to the current FAIR principle. So findable data, accessible data, interoperable data, reusable data. And so since 50 years, we do that. So, but in fact, to understand the CDS mission, we have to understand what is the data in astronomy. So in fact, the basis of the astronomy, whatever the epoch we are, we always try to observe the sky with the greatest possible accuracy. And consequently, the resulting data of these observations will always be based on the best technology on the current context. So it has been true since Galileo, and it is true today. And if we look at the Gaia mission, the space telescope was placed in orbit 4 or 5 years ago. And this instrument is in charge of mapping as accurately as possible all the stars or other astronomical objects. If the inventor of this mission had wanted to retrieve the raw astronomical data, I mean the original images produced by the telescope, the instrument, 1 zettabyte of hard disk would be needed to simply store them. So indeed, the resolution of Gaia is 1 microarcsecond, so the equivalent of a coin placed on the moon and observed from the Earth. But it is simply not possible to store such a volume nowadays, so at least for this mission. So what I mean by this is for manipulating astronomical data, we are faced with a challenge, and we always have to choose the right method to reduce its volume without losing the physical measurements of the object observed. This is why astronomers generate what we call catalogs and tables of objects. The goal is to extract from the images the physical characteristic of the observed objects. And for instance, in the Gaia mission, images only exist in the spacecraft. The extraction of the object is operated on the device on the spacecraft, and only the resulting tables are sent to Earth. So, and there are currently about 20,000 of these tables, big, small, it depends on the origin, which constitutes the basic material of the astronomical disciplines. And this represents billions of astronomical objects with their physical characteristic. And from these billions of objects, only a very small fraction will have been the subject of specific scientific study. I mean a research paper. But these few millions of objects, which a very small storage volume, in fact, represents a maximum digest of astronomical knowledge. And in fact, this balance between the volume of the data and the scientific knowledge retells the history of the CDS, but in a reverse way. I mean, at the beginning, in 1972, it was simply not possible to apply the CDS charter neither for images nor even for catalogs. The volume manipulated was simply too huge at the time to be manipulated in an electronic form. That's why the first service at the CDS focused on the astronomical objects studied only. And this was the Simbad service. And it took about 20 years before we could consider the manipulation of astronomical catalogs and tables. So, and at the beginning of the 19th, my predecessors at CDS set up the catalog service called VizieR. And finally, we have to wait 10 years more and the evolution of the internet and the technology to be able to distribute finally the images. And this is the Aladin service. So today, the CDS can be characterized by these four numbers, 3, 5, 16, and 2 millions. So the three main services, so Simbad for astronomical objects studied in scientific literature, VizieR for astronomical catalogs, and finally, Aladin for image surveys. This represents about 500 terabytes of data, mainly for Aladin, for images, and 16 operational sites or servers around the world, and about 2 million queries per day on this service. And the data collected by the CDS is the result of numerous collaborations with scientific publishers, partners data centers, mission archives, projects, etc. And our services are used worldwide, either by partner institutes, and notably the China, or directly by the end users, scientists, amateurs, and the general publics. And for this, we offer a collection of CDS clients to access to our service. Thus, the CDS provide access by classical websites, by libraries, Python, Java, C, by web widgets such as Aladin Lite, and finally, dedicated tools such as Aladin Desktop, which I will demonstrate a little bit later. Also, there are other ways to access to our data developed by our partners. For example, you will find libraries compatible with international AVOR standards. So, for example, the TAP protocol. You can also use Python libraries such as AstroPy or Pyvo. And of course, you will also find many software packages that integrates access to CDS data. So, for example, TopCat, which was introduced to you last week, if I know, or ISASky, or Stellarium, or Worldwide Telescope, or Digistar for planetariums. So all of these tools together and access to our data, we get the 2 million queries per day that I mentioned to you. So let's introduce rapidly Simbad and VizieR, and I will continue on Aladin. So the most known service of the CDS is logically Simbad. You can access it through this URL, so http://simbad-bg.fr. And as I said, Simbad contains the basic physical characteristic of the 11 million astronomical objects studied in the scientific literature. So this database is continuously updated by our team of documentalists and astronomers. And it's, in fact, a considerable work of extraction and analysis of the content of the bibliographic articles. And the current database is based on Progress, and the developments have been made in Java language. And the development is ensured by 2 or 3 of my colleagues since the beginning. So when you enter the identifier of an object, for example, M51, you will get its basic characteristics, its positions, its magnitude, its morphologic type. But you will get also the other identifiers for these objects known in the literature. And you will see that the evolution of this list of identifier will retrace the evolution of the scientific knowledge on these objects, taking into account all the wavelength of the observation from gamma or X-ray to the radio through the optics. And finally, Simbad will provide to you the list of bibliographic references in which these objects have been mentioned by one author. So now we'll go to the second service, so VizieR. This is the second major CDS service, the catalog service. So it contains 20,000 catalogs, published tables in literature or observation logs. And it is a service that is also continuously updated by my colleagues. And it is mainly based on a Postgres database. After Sybase, now it's Postgres. The developments were mainly written in C language and Java by 2 of my colleagues. And when you query VizieR, for example, by a mission keyword, so here Gaia, and an astronomical object, you will retrieve the list of tables and catalogs concerned by your query here. And from this, you can have constraints such as parallax limits, for instance, and finally, you can retrieve the extract of the catalogs corresponding to your query. The VizieR service also allows you to retrieve catalogs in their integrality if you need. And in fact, the vast majority of astronomical tools that you use rely on VizieR to get the astronomical tables that they need. Now, I arrive to Aladin. This is the last service from CDS. And the rest of my presentation will focus on this service. And in particular, the Aladin desktop tool, which I will demonstrate a little bit later. So Aladin is an interactive atlas of the sky. So in fact, it allows the user, you, to view digitized images on the sky and superimpose astronomical catalogs or data from Simbad or VizieR or other providers over your background images. And as Aladin clients requires a certain degree of dynamicity to manipulate the display image, you have to zoom, you have to pan, a simple web page was not appropriate, in fact. And the first version of Aladin was released in the late 2000s. It was coded in C++ and was based on the X11 technology at this epoch. But this version did not really go beyond the prototype stage because a new technology totally disrupted the first choice. It is the advent of the Java language, and notably the possibility to make applets. So the applets technology allowed to build dynamic interface inside a regular web browser. It's very common today, but at this epoch, it is really a revolution, and we are able to do some rich interface inside Microsoft Explorer or Netscape's browser. And in fact, it was my first development at CDS within the Aladin team. So the Java technology proved to be very efficient, and we quickly decided to extend the Aladin usage for all our users. And since 2003, Aladin was available both as an applet inside your browser and as a standalone application requiring a classical installation. And it was the same code, but the standalone installation was not limited by the security restriction of the applet. and allow, in fact, a more efficient usage for the users. And this strategy choice, an applet and a standalone version, persisted for the next 10 years, and Aladin's success was consolidated over this period. But as with many technology choice, it is not always possible to guarantee the durability of our decisions, and especially when elements are not under our control. And in the case of the Java language, we had to face a strategy battle between Oracle, owner of the right of the Java language, Google in its deployment of Android, and Apple following its own strategy. And in fact, the applet solution, which was very powerful in our context, was discredited at this time, and the web browsers maker have no longer supported it. So to respond to this evolution, we decided to start a new development called Aladin Lite, and this time based on JavaScript language, in order to replace the original Java applet. And while keeping the Aladin standalone application, now called Aladin Desktop, continue to its life. So in last month, in November at ADAS conference, my colleagues, Thomas Borth and Matthew Bowman, demonstrate the latest version of this Aladin Lite development, which now use TypeScript language and Rust to take advantage of graphics card acceleration libraries. Okay, but currently, so Aladin Sky Atlas is available in two complementary applications. Aladin Desktop, offering the most functionalities but requiring prior installation on your machine, and Aladin Lite, directly usable inside the web pages and offering the basic display functionalities. So the rest of my presentation will only concern Aladin Desktop. As I said, the beginning of Aladin Desktop development started in 1990. And at present, the code represents 5 megabytes of executable bytecode, or 250,000 lines of source code. So the Aladin's code has the particularity of relying only on Java libraries written by the CDS, and only the original Java libraries are used. The main reason for this choice comes from its history. In fact, in 1990, there were very few libraries available. So in astronomical discipline, but also for the displaying of images, this kind of thing. So we had to write them by ourselves. And in fact, today, this choice offers us a great flexibility for our current developments, because we have all the control of our code, whether for the innovations or for controlling our distribution and associated licenses. So, Aladin Desktop developments over the years have mainly employed 5 developers from the CDS and dozen external contributors to the CDS. Its usage has been relatively stable over the last 15 years, around 1,000 sessions per day. And the number of queries generated by Aladin Desktop on the various service providing data is regularly increasing and currently represents 180,000 queries per day. And to finish with this introduction to Aladin Desktop, and before making a small demonstration, here it is an overview illustrating the 22 years of existence of these software tools. On the top left, you will find a copy of my study notebook in the beginning, showing my ideas for the Aladin interface. And at the bottom right, you will find a screenshot of the latest version of Aladin, so the release 11, which still incorporates, in fact, many of the ideas that were imagined at the time. Okay, now I will try a demonstration. I prepared for you a short video that I will comment, because I'm not sure that the download and upload the link from home will be enough. I hope it will work. So it is there. Okay, I hope you can see my copy. Here it is the Aladin interface, and you have on the left side, the resource tree. I will come back on this in the second part of demonstration. And on the right side, the stack system, which hosts the data that you will load. And now I will access to the data servers on an old system just to reproduce the story of Aladin. And I will load an image from VizieR servers, so our NASA colleagues, around the galaxy M51. And I will choose surveys, so digital sky surveys, for instance, the DSS ride surveys. When I do that, Aladin will query VizieR databases and ask to generate images, and this image is arriving in these stacks, and you will be able to manipulate these images by zooming, panning, etc. Obviously, the goal of Aladin will be to overlay this image by tabular data or Simbad data. And here I will load Simbad results over this field. I will just adapt the radius and the position to be sure that it is covering my full field. And I query my Simbad servers. I will change the filters for having just small circle corresponding to each Simbad objects. Here it is. And I will be able to manipulate the stack on the right stack and to change the order if I need to overlay the front or the background of the stack. And now, if I select objects, I will have the possibility to retrieve the full characteristic of each Simbad objects and see where it is in the field. And here I will select all my objects. I will sort my tables by bibliographic references to find the most cited objects, so it is the main galaxy of the field. And if I click on the link, I will arrive to the original server, so Simbad web page, and I will retrieve what I have presented just before, my basic data for these galaxies, and the various elements, so the identifier. And if I go on the bottom of the pages, I will be able to load the reference bibliographic, the bibliographic reference for these objects. So I will reduce a little bit the range of the years to have no too many results. And here I have all the results. And in fact, all these results is reincorporated by our partners. If you query ADS, you will find, in fact, Simbad results for the objects. Now, I will show you briefly some other basic function of Aladin. So you will see in the toolbox that you can have graphical tools, so to do some measurement, to cut through the pixel value, to do some photometric extraction and statistics like this, or to generate labels or various tags on your images. So all these features are quite easy to use. I let you to test if you need. Another important thing in Aladin is the goal is to be able to compare data. So to compare images, to compare catalogs. And for instance, I will compare this image from VizieR to Sloan images. So I have split my screen in two panels. And I will now call Sloan archives to retrieve another images for the same galaxy. So here it is. So I have the Sloan tab. I will query on the same fields. And it will retrieve the list of available images for this field with the field of view that you can see in overlay on the left side. And I will ask VizieR to load one images, the G band of these surveys. And the result will be arrived in my second panels. in their own projection. So it depends on the rotation of the telescopes and the way that the image has been reduced. But I can, with the magic match button, adjust the two projections to have exactly the same orientation and zoom factor to be able to easily compare them side by side. And obviously, I have the possibility to overlay these two images by my tables, Simbad, or another catalogs. And for instance, to finish with this first demonstration, I will try to load another table, so Gaia, for example, the Gaia DR3, available since a few days. I will query around the region of my surveys, like this, and I will retrieve all the measurements of Gaia in the field, and I can compare quickly with, for instance, Simbad results that I have presented just before. I will not enter into the detail of all the features that you can do by Aladin. Just have in mind that Aladin is dedicated for image and catalogs and some graphical tools. So you will have in the image menu, in English, sorry for Chinese people, some advanced feature to manipulate the pixels, for instance. Here it is the way that you adapt the contrast or the color map, but you can also do some computation of pixel to do convolution, addition, arithmetic operation, in fact, or extraction of pixels, or blink system to compare two images, or to adjust the astrometric solution of your images, or you can directly access to, for instance, a small slider to see in transparency the two images on the same field. And you have the same things for catalogs. You have a few basic functionalities to manipulate catalogs in the second menu here. You can do some cross-match in the catalogs loaded in Aladin, and you can also do some filters. A filter is a very powerful functionality in Aladin, allow you to control the way that the objects are displayed on the screen. So you can control, for instance, I want to draw only some stars or galaxy, draw an arrow proportional to the proportion of stars, the size of the LP of the objects, etc., etc. And so you have to read a little bit the documentation because it's based on a script system like this, and you can apply this way to display the catalogs either on an individual table or on all the stacks that you have loaded. Okay, I think I have already presented the graphical tools, so the photometric tools, the distance tool, and some addition. Obviously, you can draw some grids, so coordinates grid, for instance. And like this, I will show you the coordinates grids. And I will present some advanced feature in Aladin in the second demonstration. So I will come back to my talk now. There it is. Yep. And now I will continue my talk. I focus on an historical, very important revolution or evolution of Aladin tools. I mean, in 2005, 2010, the IPS revolutions. So, in fact, in 2005-06, we saw the advent of new astronomical software that disrupt our usual practices. So, two major players in computing games, namely Google and Microsoft, both came out with their astronomical image display tools, Google Sky on the side and Worldwide Telescope, that allow you to move in the image of sky survey as easily as if it were a simulation tool. So you can pan, you can zoom from very wide fields to extremely accurate fields. Everything became possible with a simple laptop and an internet connections. And this is the Google Earth effect. It has profoundly changed our practice. And it was no longer a question of loading individual images, as I have presented just before, but of providing global access to a sky survey. And to be perfectly honest, this revolution has begun a little bit earlier, in 2001, by the first prototype called Virtual Sky by our colleague Roy William. And for us, it was clear to us in this epoch that we have to follow this revolution in Aladin. So it was interesting to realize a posteriori now the reasons of the emergence of such evolution. In fact, to achieve this new method of access images, 4 challenges must be addressed. How to manage the volume of data that is necessary to download to the client, in fact, and will the client software be able to display this data quickly and efficiently enough for a dynamic display? And finally, how to organize this data, these pixels, and especially how to reproject these individual images in a coherent system, a big mosaic, in fact. And when I started at TDS, the sky surveys called DSS, so the Digital Sky Survey, was stored in our machine room in a huge box with the robots loading the disk, extracting an image. Took about one minute, and a half minutes. And transferring such an image over the internet, again, took several dozens of seconds. So we couldn't do better that image by image transfer. But in the first decade of the 2000s, both the internet and storage media logically followed the evolution of technology. And what was impossible in the 90s became possible. And in fact, the DSS is a collection of images of the sky at a resolution of 1 arcsecond pixel, which represents 500 billion pixels, or 1 terabyte of data. And it's not so huge. In 2005, this volume of data became compatible with a totally different usage of this image. And we were able to resample the entire surveys to produce an overall coherent system, a huge mosaic, in fact. And I will come back on this mosaic later. And at the same time, the internet and its development in the population was now offering sufficient support to distribute this pixel at a good rate for this new type of display. And at the same time, the technology used in the graphic cards was becoming powerful enough to manipulate a large volume of pixels in a few milliseconds. Thus, we were able to display in less than 10 milliseconds a collection of thumbnails, what we call tags now, to dynamically manipulate a view of the sky. And the operation that took several seconds 10 years ago before was now done in a few milliseconds, in fact. Therefore, since the volume of the data and the client's performance were no longer insurmountable, it becomes possible to build a global coherent system to generate and allow rapid access to a global mosaic previously built from the original image surveys. So now the images are generally flat. It's a matrix of pixels, and the sky seen from the Earth spherical. It is the celestial sphere. So therefore, how to build a spherical global mosaic? And this is the last challenge. And in 2006, the CDS arrived shortly after the battle. Google has adopted the same division as Google Earth, so based on cylindrical projection. Microsoft have opted for triangle division based on toast system, and we voluntarily opted for a solution that guarantee a good preservation of the physical properties of the pixel. And we invented at this time the HIP systems based on the LPX tessellization of the celestial sphere. So I won't go into HIP's details, but just the important things to remember is that system allows the user to move around a full sky survey, just like it's possible in Google Earth. And this method can be applied to images, but also to the astronomical catalogs, or even other type of data. And the method avoids as much as possible the distortion related to the spherical projection of images and allow access to all the dynamic of the original pixel. So it's clearly a scientific purpose. So in concrete terms, HIPS will consist of a pre-calculation that is performed once for all, and it consists in reprojecting all the pixels of the original images in an LPix grid at the appropriate resolution, and the resulting pixel will be packaged into tiles in the form of classical images file, JPEG, PNG, or even FITs to preserve the dynamic of the original pixels. And this collection of tiles will be stored in a classical file system and distributed via an HTTP server. And this very simple and flexible architecture will be clearly the key of the success of HIPS. So in 2010, we were able to demonstrate the first prototype based on the HIPS method, and we had developed code to generate HIPS, so HIPGen, and Aladin was able to display such a HIPS. And as a result, several clients were developed, both from CDS, such as Aladin Lite or Aladin Desktop, and from external partners, such as VizieR from CNES France. And the success was rapid, and in 2016, the International Virtual Observatory Alliance decided to endorse this method in a form of international standards. So in today, in 2021, HIPS is not only an international standard, but also a set of collaborative servers, so 20 servers managed by different institutes, and distributing the types of HIPS surveys around the world. It is also a dozen of clients able to display this HIPS data. And these tools share different niches for scientists, such as Aladin, for amateur astronomers, such as Keystar, for planetarium displays, such as Digistar or Wide Telescope, or even for the general public as a Stellarium, for instance. And a large majority of sky survey display tools today have now adopted this technology. So finally, HIPS is more than 1,000 surveys of the sky, and finally more than 800,000 requests for tiles per day from the various tools that I have mentioned. Now, my second demonstration, very short before my conclusion. Where is my... oops. Okay, my second demonstration here. So now I will demonstrate the HIPS usage. So on the left side of Aladin, you will have these new things called the resource tree. It allows you to access to all available data over the world. So the HIPS, the thousands of HIPS, but also the catalogs from VizieR or from any VO servers. And here I will load the DSS color, but not image by image, but directly the HIPS results from the DSS colored surveys. And here I have the results, so it's Orion fields. And as I said, I will be able to zoom and pan into the whole surveys as easily as you did with Google Earth or other tools, equivalent tools. Okay. For instance, I will zoom a little bit on the Pleiad. I will just change the projection of the reference to switch in galactic mode. And now I will zoom a little bit on M45. And I will zoom in until reach the limit of this survey, so the 1 arcseconds per pixels. So you will see that it is extremely easy now to play with Aladin because you haven't to manage image by image, but you go through the whole surveys. And as it is just a projection of tiles, you can change the default projection. So now I am in a spherical projection. Before I was in 8-off projection. I can choose a stereographic or tangential. It's not a problem. The graphic cards will do the job for you to display the tides according to the current projection. And I will now compare. In fact, Aladin allows the same functionalities in HIPS as I have presented before for individual images. For example, here I will jump in Andromeda galaxy, and I will load another HIPS surveys Pan-STAR. So Pan-STAR is a huge survey. It's 25 more than the DSS original surveys. It arrived very efficiently, and now I was able to compare by transparency or side by side. As I have presented before with individual images, I do exactly the same things with HIPS systems. If you see that, you can think that, in fact, I will just show you just before how the tides is managed in Aladin. So you see that the tides arriving depending on your internet connection, and I will just come back to the full sky Pan-STAR, and now I will load the, wait a minute. I will load a cheat code, trace just to display the border of the tides, just to show you how HIPS is used in Aladin. And you see here that if I zoom, the tide is arriving according to the current field that I am displaying. And it is the same usage in the other tools, the Worldwide Telescope, Digistar, Stellarium, which use HIPS. Now, I come back to a full field, and I will show you just for the end of my talk that HIPS is not just dedicated for global surveys, such as digital sky surveys or Pan-STAR, but you can also generate a HIPS for pointed survey. And for instance, if you take a telescope such as Hubble, Hubble is a spacecraft with a very accurate instrument, so it's not possible to cover all the sky, just pointed observation. And but it's possible to generate a HIPS mosaic based on this collection of images. And here I will load the Hubble Space Telescope for the B survey, the B band, sorry. I use my resource tree in Aladin on the left side, and I will load the progressive, so the HIPS survey. So, and as I said, there is mainly nothing in the sky, just small patchy observation, because there is, in fact, a very small coverage of the HST cells, but with the accuracy of the HST. And if I move on Andromeda fields, I will just show you in transparency the DSS, and you have here the full resolution available in HST. Okay, I think I have just finished. I will stop my video just to avoid to be too long. I will let you to discover the various features that you can find in Aladin, and I will conclude my talk. Wait a minute, I will stop there. Okay, come back to my presentation. There it is. So to conclude, I would like just to draw your attention to 3 points that I hope have been transparent in my talk. And first of all, I would say that technology is never first. The first thing is the data, the knowledge. And this is the more important. And a technological solution that lost the physical quality or the physical characteristic of your data will probably fail and is not adapted for our purpose. And secondly, it is, I would say, prudent to rush slowly toward a new technical solution. There is clearly the fashion effect in our communities, but that doesn't mean that the solution for one day will have a long durability. And in fact, there is no urgency to choose the latest technology. But on the other hand, it is essential to not miss some deep evolutions of the technical context. And typically, the evolution of internet, capacity of credit cards, I have explained before. And one of the most effective ways to ensure that this is just to simply let yourself to be surprised by newcomers, and notably the young developers of your teams or of your work. And it is a quite natural solution to let open the door to necessary evolution. And I think it's enough. I hope you have follow my talk easily, and thank for your attention. And if you have questions, I'm ready for that.